So, good afternoon. Welcome back after this short break. I hope you enjoyed the keynote presentations. I found them really very interesting, and we will continue with interesting topics. Now we will move to the technical sessions, and as I mentioned, it's going to be quite dynamic. Each author has only about 3 to 5 minutes to present their work, so that's one request. Please try to keep the time so that we will manage everything in time. And just for your information, there is a small change in the program. We will start with the second presentation. So I'm happy to welcome Patrik Horažďovský, who is going to present his dynamic public transport planning in a real environment. So Patrik, the floor is yours.
We will start the second presentation. So I'm happy to welcome Patrik Horažďovský, who is going to present his
I hope that you can hear me well, because I hear this presentation twice. I am glad that I can start this section. So my topic is about public transport, about dynamic public transport, and I want to present you my opinion how we can implement that dynamic public transport to the real operation. So in the first, it's me and Professor Svítek, who's an author of this topic, of this paper, Scientific. So this is the first point. It depends on my dissertation work named Dynamic Service by Public Transport in the Region. So this for the start. The problem is known. It's the problem of public transport in the region. It's called a last mile problem and other problems, and it depends to lack of the transport connections. There are some small municipalities in region, and it's very hard to serve them. There are problems with big vehicles, big capacity of buses, for example, and there are no passengers, or there are passengers who want to be transported, but there are not connection because it's too expensive. So there are many problems, and with these problems there are some dissatisfaction of passengers, and they use the cars. And if we know that there are a problem with cars in the cities, so we have to help them in the region, because there are many passengers from region who want to go to the city. So I want to use some smart organization of the public transport, and I created the dynamic public transport, and I wanted to share multiple modes of transport and things like that. I can speak more, but I have only 3 minutes. So for me, there are some interconnection about all modes, about information, about data, and this is the smart approach and smart connection to the region. So that is the dynamic public transport, but we cannot make it dynamic for a whole system. You can imagine that you are in the city center and you have to call, for example, for metro. It's impossible. So we have to deal with the problem: where is that dynamic place, where is the dynamic region, because it's not possible to implement the dynamic thinking in the whole region. So I divided it into 3 levels. I tried to draw some pictures. So the first one is it's an image with the main line. It's a main bus line, tram line, or maybe the train line. The second one is the second level of lines. So it's quite there are many villages, but it's not the third situation where there are too much villages that we cannot make the lines practically, that we create the lines which have too long times for travel, so people are disappointed. And so I created the 3 levels, and the third levels, there are some dynamic parts, and in these parts I want to implement the dynamic lines. And what is the dynamic line? It's line, simply public transport line with a road and time position, which is which dynamically change. It's not the timetable, and we will call it is or not, it is in operation or not. No one will call it's not. If yes, it's in operation. This is different. There is whole service is depend on some demand and some other parameters. In the next slide, there are the parameters I want to discuss. It's some demand, some offer, infrastructure, maybe some ecological problems, and etc. But for me, the main parameter is the obliquity, row deviation, and in the pictures here and here, you can see that normally the line goes straight, but there is something that we can call row deviation. And if that row deviation is about 10 minutes, the people who use whose use this public transport are not satisfied because they are 10 minutes more in the bus, and with maybe with no, that's not good for them because they are 10 minutes late, for example, in their work. So I create some coefficients about lost time and lost distance, and if the coefficient it's in some level, I can say yes, this line is in the third level. It's the line with dynamic parameters, and I can say yes, if we have these conditions, this can be implemented, and the dynamic can be implemented to this region and by these lines. So I chose one place, one region in Prague. It's Radotín Černošice, and there is line 313, and it's sure that there is many problems, and I wanted to implement this dynamic. So that's my example. You can see some places with dynamic place. They should be served by something else, and the blue one, it should be the normal line, which is fast. Also, the efficiency, that's a point, that's a new parameter I created. So that's a parameter I created for choose which one route is perfect for these parameters, for this demand, for this time, and etc. So parameters, time, demand, etc. they are in this efficiency. So after that, I create some model. That model was in the multi-agent system in Analogy. It's programmed where I created this model, and I tried to create some agents which negotiates between us and create some result. The result is here in the right. There are the best solution where we can say where we can see which bus stops are connected to the dynamic line in this solution in this time. So we can see how much passengers there are on that stops, and we see that they don't serve the third bus stop. So it's about simulation, and there are some results, depends on efficiency and the other parameters that I spoke about. So that's the last slide where I can say that the project is designed and the dissertation is completed, and I want to evaluate, and I want to develop some algorithms and parameters, and I want to cooperate with carries and public transport organizations, and I want to implement this approach. So I hope that this will be successful, because this cooperation is now in progress. So I hope so. So this is the end. I had only 5 minutes. So if you have some questions, maybe I can answer you.
Patrick, thank you very much for your presentation. Well, we just demonstrated that it's really a challenge to keep the 3 minutes, but I am afraid there is not much time for additional questions now, but you will have all the presentations available on our website latest tomorrow, and there will be contacts to all the presenters, so you will have the opportunity to ask Patrick if you find this topic interesting, which I certainly do. We will continue with the topic of city or smart city modeling, which is, in my opinion, really crucial topic. And the next presentation will be done by Roman Dostal, also from the Czech Technical University, who is going to talk about city simulation software. So, Roman, welcome, and please try to think about the time and keep the 3 minutes deadline. Thank you. The floor is yours.
Certainly. Thank you, and greetings to everyone. My name is Roman Dostal, and I would like to briefly summarize the findings of the project Artificial Intelligence for Cities and Regions, which is led by Professor Svítek, which is a sub-project of the National Center of Competence of Artificial Intelligence and Cybernetics, which is led by Professor Mařík. Next slide, please. Due to some technical difficulties, I am not able to see what is being shown, and I cannot control the presentation, so hopefully everything is all right. The fundamental idea is based in combination of the 4 most prominent areas of expertise in a city, which in this case, from our point of view, is energy, urbanism, environment, and mobility. And in the center, there is the area of focus that is chosen, and the area that is modeled and compared throughout different scenarios. All these areas of expertise and the models are then combined in the city simulation software, which is a platform that integrates and combines all these environments. Our scope of work, the part of the Faculty of Transportation Sciences, is the scope of mobility modeling and integration with environmental modeling. Next slide, please. Now, the integration among mobility and environment was done first by modeling everything in SUMO, which basically includes creation of the infrastructure. It includes creation of OD matrices, inclusion of driver behavior, inclusion of vehicle mix, and other stuff as well, of course. And the inputs, the outputs of the modeling of SUMO were in well-known text format for the infrastructure and XML for the values that are modeled in SUMO. In QGIS, and this can be done in any other GIS-compatible software, these 2 outputs, the well-known text and the XML, were paired for each scenario, and then exported in shapefile, and it can be any other format that is then integratable and compatible with the environmental modeling, which was done in PALM. Next slide, please. And since I cannot see, I'm sorry. Yeah. The area that was chosen was Evropská Street from Vítězné náměstí Square or the Kulaťák roundabout up until the train station Nádraží Veleslavín, which is a sub-area of a greater endeavor, a greater project, which is led by SmartPlan and in cooperation with Czech Technical University in Prague and other partners, institutions, and companies. That is called Smart Evropská. But for the area of this project in particular, only the area from Nádraží Veleslavín and Vítězné náměstí was chosen and modeled throughout all the different areas of expertise. Next slide, please. And now you can see the outputs, the experts of SUMO, which can be not only in XML or tabular form, it can also be exported in already a visualized manner. In this instance, it's heat maps that show for any particular time period the individual key performance indicators throughout the entire area. This allows for an easy visual comparison among the different scenarios, and of course as well, since it can be exported in XML, it can be analyzed, the data can be analyzed automatically through the values. Next slide, please. I'm sorry, I'm a little lost in what is being shown right now. Yeah. Now you can see the simulation of the traffic. It's the same exports from the Sumo, but now visualized in QGIS environment, which allows for a user-friendly and high variety of possible visualizations of the data. And it also enables us to conduct a spatial data analysis, which can be very beneficial if we are considering, for example, globalized key performance indicators through the entire area to better compare the individual scenarios. Next slide, please. Here you can see the example of what the city simulation software looks like. It combines the individual models, it combines the individual area of expertise, and bands them together in this platform, which is called city simulation software, where we can easily compare the individual scenarios throughout the models. And there's not only the visual representation of the data, but also a globalized data as well throughout all of these models. Next slide, please. To conclude, with the exports from Sumo, we are able to analyze data from the entire area in a tabular form. The exports are in XML and can be analyzed in numerous softwares for data analysis or database softwares. The data can also be subjected to spatial analysis in GIS softwares. It can be either QGIS, which is a freeware, or it can be ArcGIS or other GIS softwares. After pairing the data from Sumo, that's the well-known text and the XML outputs, and therefore the integration of mobility modeling is possible with the environmental modeling, which in this case was Palm and Sumo, through an intermediate, which was in this case QGIS. The goal now is to find ways to verify the models. It's to find additional ways for intermodal integration and find ways to globalize the KPIs to compare the scenarios easily. Thank you. That's all. On the next slide, that's only my goodbye. And thank you for the attention. And I'm sorry for the technical difficulties which caused a little bit distress. Thank you.
Thank you, Roman, very much. I really could appreciate you were trying to keep the time, so thank you. We have not received any questions, so we will move to the next presenter, which is Sumer Anis from Italy, who is going to talk about another very important topic, and that's actually public transport accessibility index. And we have been working together with architects, and this was certainly one of the crucial issues that should be dealt with. So I'm really looking forward to your presentation. The floor is yours.
Okay. Hello. Hello. Okay. Okay, so I can start. Okay, thank you. Okay. Hello, everyone. My name is Sumer. I'm from University of Genova, Italy. Today, I'm going to present you a brief overview about my research, which is about the methodological framework for the determination of public transport accessibility index. This presentation will go on by defining the basic objective why we carried out this research, and the most important part is by defining the scale of measurements and what scoring system we have used, along with a practical application of this research by a numerical example, and then a special aspect of this research, and then the conclusions. The basic objective of this research is to increase the performance of the public transport. When we talk about the performance of the public transport, there are many aspects like accessibility, connectivity, availability, and etc. And one of the most important aspects of the performance of the public transport is the connectivity. And when we talk about the connectivity, it's about the connectivity to the maximum possible population, like how many people are able to use the public transport, and how well a public transport is connected with the regions to the destinations. These regions to the destinations, we use the term as the service centers, and how much public transport is connected to the nearby regions. Like if someone has to travel from one region to another region, how well established is the public transport in terms of the regional connectivity. So based on all these criteria, we have introduced a unique scoring system based on the entire network of public transport, and to highlight the least accessible areas. So in order to talk about this scoring system, first we have to understand the scale of measurements. Because this framework provides the values, one for each unit of the scale of measurement. So we have used two units of the scale of measurement. One is the inter-regional and the inter-regional level, another is the inter-regional and regional level. In this level, the biggest unit of measure is the city boundaries, which means that the one city is considered and divided into many parts, like for example traffic analysis zone and other smaller boundaries, and then the values are calculated for each smaller unit. And in this scale of measurement, the biggest unit of measurement is considered as the regions, and then the regional boundaries, as you know, is right into the city boundaries, then the district boundaries, and the values are calculated accordingly. If we talk about the data sets, these data sets are generally required to apply these frameworks to any city or any region. So if you have these type of data sets like administrative bodies, population, public transport network, population densities, and the service center information, public transport nodes information, then you can accordingly define the level scale of measurements, and based on these data sets, and you can apply this methodology to any network of any region. As far as the scoring system is concerned, there are three main pillars of the scoring system. First one is the proximity to the public transport, then access to the service center, and finally the proximity to the nearby regions. The proximity to the public transport, it depends on the type of the stop. As we know that one stop can serve as in many functions, like it can be only the bus stop, or it can be a mixed node with bus stop and the metro station, and it can be the regional stop. So based on each stop, the recommended values have been used from the literature to draw a walking distance network buffer around each stop and to capture the population. So accordingly, the proportions are defined, like how much population are falling under that buffer, and the relevant scores are calculated. Then based on these scores, the maximum of each these criteria will be taken into consideration for the calculation of the final value of the public transport accessibility index. Similarly, the access to the service center has been calculated in the similar way. When we talk about the proximity to the nearby regions, then the 1,000 meter walking distance buffer is has been drawn around the centroid of each smallest unit of measurement, and it has been seen that how far can you go from the center of the smaller unit of measurement to the bigger smaller unit of measurement. Of course, because we are talking about the public transport, so we will only consider public transport stops, not the road networks. So it will capture the number of public transport stops which fall under this network distance buffer, and the relevant score is directly being utilized for the calculation of public transport accessibility index. In order to see the applicability of this defined framework, we have used a small dummy example to see its practical usage. Like a smaller region is defined, and it is divided into the five cities, and the characteristics of each cities, it's been defined according to the population and the bus line. There are two bus lines, one metro line and one regional connection. Then we have used the node 18 to just to present you the calculations, like how we have calculated the public transport accessibility index. The reason for this node 18 is selected because it is a multimodal node which serves different functions when crossed by different lines. Like it is regional and the local connection crossed by the bus line and the metro line, and it only serves as the regional connection when crossed by the railway line. So by applying the each criteria in the scoring system separately, the public transport accessibility index has been calculated for each cities. Since here we are using the scale of measurement as intra-regional and the inter-regional level, which means that the biggest unit of measurement is the region. Then the region is divided into 5 cities. So that's why the value of PTI, there is one value of PTI per city. As you can see that the value of CDE are less as compared to the value of ABC, which means that CDE are least accessible cities as compared to the B. It is very interesting to see that like the value of the public transport accessibility index for the city B is the maximum. But is it really the maximum? As you can see the size of the city B. So let's imagine we have divided the city B into the more smaller regions according to the traffic analysis zone 1 and 2. Then if we apply the same criteria again for each traffic analysis zone, then we can see clearly that okay, the city B was not entirely accessible. This traffic analysis zone has least accessible as compared to this traffic analysis zone. So this shows us the importance of dividing the cities and usage of the smallest units of measurement as available. Because if we identify the smallest possible area, then we can comment on the performance of the public transport in a correct way, and we can improve the public transport by using the different methods. Finally, we have concluded that this framework is efficient in terms of showing us the performance of the public transport, or it is efficient in the evaluation of the performance of the public transport. Since only the public transport attributes are used, so we can confidently say that this framework is ready to be applicable to the public transport of any regions, and also because of the travel times are entirely based on the network of the public transport. Also, we use these results to overlay on the map of a region or a city or like a smaller district in the city, and we can show the least accessible areas. So what is the purpose for a representation of these least accessible areas? These least accessible areas can be used for the many future analysis, which is connectivity analysis, cost benefit analysis, public transport network optimization, like many other analysis. So it gives us a way, or it opens a new ways towards the new research. So this map can be used as a base layer for the future analysis. Also, the one of the most major usage or the application of this framework is in the public transport assignment models. We have used the distance and calculate the travel times based on using the different tools in ArcGIS. But these data can be directly used from the OpenStreetMaps. In this way, this data will be more accurate and the travel time will be more realistic. And the least accessible areas can also be served by introduction of different alternatives like public transport plus car sharing system or demand responsive public transport system. Like there are many different approaches which can be way forward from this research. Thanks a lot. That's all from me.
So thank you very much for your interesting presentation. I wish you really good luck with your work. I consider this topic to be very important, so good luck. And the next presentation is going to be by Ondřej Paprčka, who is from CTU, and he's going to present results of a driving simulator and actually the influence of critical situations on heart rate changes. So the floor is yours. Thank you.
Thank you for the introduction. As said, my name is Ondřej Paprčka. I'm from CTU, and my article is Heart Rate Changes in Critical Situations in a Vehicle Simulator. This article is about a study of heart rate changes of drivers in a vehicle simulator when they are confronted with potentially collision. And the aim of this study was to determine the probability of a significant increase in heart rate after the critical situations, and whether measurement of heart rate in simulators can be used as an indicator of critical or stressful situations. Overall, there were 30 participants from different backgrounds and of different ages. The equipment that was used was the vehicle simulator was the Škoda Superb cockpit. an automatic gearbox, all electronic assistance systems were disabled, and the virtual scene was displayed on 3 screens all around the simulator. For the measuring device of the heart rate, the Wahoo Ticker X chest strap sensor was chosen. It uses non-invasive ECG technology. It has electrode levels. It uses and plus, and we used pulse monitor processing software. Other devices were tested but not included in the study. In the end, there were some issues with motion artifacts and some other errors. The simulation scenario consisted of a highway track with 2 lanes. There was the standard speed limit, the Czech standard, 130 kilometers per hour. Each participant had approximately 6 minutes of free driving, followed by 2 minutes of following a truck and a car, as you can see in the pictures. And then the critical event happened, which was that a cargo box fell from the cargo hold of the truck that the driver was following. For the evaluation, we used 8 calculated parameters. The first 3 primary parameters were the first part parameters, and they were designed to determine whether there was a significant increase in heart rate after the beginning of the critical event. So basically to show us if there was any significant increase at all. And the second part parameters were 5 secondary parameters, and they were designed to determine whether the increase in heart rate was connected to the critical event itself, or if it was brought on by some other things. Here we have the overall results. There are many more preliminary results, but since we have not much time, then here are the overall results. Basically, 43% of the participants do not show any significant increase in heart rate, so they failed the first part. Then further, 11% of participants show at least some significant increase in heart rate, but the probability that it is connected to the critical event itself is very, very low, since they failed all of the secondary parameters. Then 32% of participants show some significant increase in heart rate after the critical event, but it is still questionable whether this increase is connected to the critical event itself, because they failed some of the secondary parameters. And then we have the 14%, which have a very high probability of being directly affected by the critical event and show a significant increase in the heart rate. As you can see from these results, it is questionable if heart rate measurements can be used as a source of objective data. Primary data, I would say that the implications of this study are that it is not really advisable to rely solely on heart rate measurements in a vehicle simulator in critical situations. And I would that's basically it for my brief presentation. I hope I managed the time limit, and I would say that this study was also done because there were not really any other studies that concern this topic. So I think it fills a gap in our understanding of critical situations and heart rate monitoring in vehicle simulators. Thank you.
Thank you very much. I found it really interesting. And maybe one quick question. Do you have any plans to continue with this research and maybe validate these results in some real-world situation, even though I'm not sure how to do that?
Yes, there are many possibilities of many other studies to do based on this, because this is just a primary study that we can build on. So yes, there are plans to do some more research in the simulator, and then perhaps in the real world, but that's probably a longer way out.
Okay. Thank you very much for this presentation, and good luck with your work. And the
Thank
next
you.
presenter is actually Matej Kulčár from Budapest University of Technology and Economics, and he's going to talk about gravity model, how and the changes when you use services related to automated and autonomous vehicles. So please, the floor is yours.
Thank you very much for the opportunity. I would like to welcome everyone. I'm Matej Kulčár from Hungary. We have carried out the research in the field of autonomous vehicles. Because of the spread of the autonomous vehicles, new planning methods are needed. We have developed autonomous vehicle-based mobility service, which can ease the procedure of the commuting. The motivation of our research was to identify whether Newton's gravity model can be applied for the analysis. The proposed mobility service provides door-to-door transfer. It is a suburb commuting service. Microcars, which are coming from the different parts of the city, board the trailer collection point, and they get off the trailer at the distribution point near to their final destination, from where they make the last kilometers on their own. Our method is based on a multi-level analysis using a gravity model. The value of the interactions between the zones and the cities give a necessary number of the collection point. At the macro level, we determined the number of the collection point for the cities, and at the meso level, it is determined for the zones. In the analysis, we took into account the population and the job opportunities of the city and the spatial factors, which can help to analyze the extent of the pressures of the high and low capacity public transport in the city. In the analysis, we also took account in the willingness to switch between commuters for the mobility service. Furthermore, the peak hour capacity of the collection points and the degree of the motorization of the area were also taken into account. The basic gravity model is shown on the slide. The original gravity model, including a gravitational constant and the gravitational factor, which can be directly or inversely proportional to the intensity value. At the macro level, we introduce new factors such as the time factor, commercial demand factor, or the strength of public transport factor. At the meso level, we analyze the accessibility between zones and the pressures of the high and low capacity public transport in the city. It is necessary to examine the pressures of the public transport because the mobility service is not intended to distract passengers from the public transport. With gravity models, our goal is to explore the future needs for the mobility service. The main result of our research is a creation of these gravitational model formulas supplemented with these factors. The case study was conducted in Budakalász. The city is located in the agglomeration of Budapest, so the capital city has a significant effect on the analysis. During the case study, we took into account the high-capacity public transport connection between Budapest and Budakalász. The city was divided into the zones. We have created an autonomous vehicle-based mobility service to improve commuting phenomenon. We developed a number of the collection point determination method using gravity model to we introduce new variables into the models for more accurate analysis, such as the time factor or public transport factors. The interaction values between the cities and zones give a required number of the collection point. And we applied a method to the city of Budakalász, and the result is that 23 collection points need to be established in Budakalász. Thank you for your kind attention. I'm looking forward to questions at the end of the session.
Thank you very much, Mate. We have not received any questions. I believe the topic is clear, and I guess everybody will look at your paper if there are any additional questions. So good luck with your work, and thank you.
Okay.
The last presentation of this block is going to be done by Mr. Václav Řehoř, who is from the Prague airport, and he is going to talk about smart airports. So I'm definitely looking forward to this final presentation. So please, the floor is yours.
Good afternoon, everyone. It's my great pleasure to be a part of the conference. Thank you very much for the invitation. I'm here representing a team composed of a couple of airport workers and the Technical University in Czech Technical University in Prague. Entire team is led by Professor Svitek. We've been talking about smart cities and smart airport for a while, and we looked at the smart airport slightly from the different angle. There is a concept which got 4 levels. When you look at these 4 levels, you'll find that Airport 1.0 is basically about ensuring a safety and efficiency aircraft operation. There is no much interaction with the surroundings, with other systems. Quite a lot of airports are still unfortunately operated and called Airport 1.0. Then we moved to second level, which is a supply system services. It can be divided. It depends on the advanced work at the airport between these 2 levels. And you can see that there are a lot of new technologies being implemented at the airport, and quite a lot of information is shared among all the stakeholders, which definitely is offering higher performance of the operation, and it starts improving the passenger experience. Then when we move to the next level, which is Airport 3.0, all the stakeholders are fully connected. When I talk about those stakeholders, I mean air traffic control, ATC, handling companies, airlines, and airports. These are the main 4 stakeholders fully connected all together. And of course, all the information has been exchanged in real time, which is a great advantage and a way to increase the passenger experience and definitely to be more efficient as the airport. And then there is Airport 4.0, which is slightly different concept. When you look at it, it's more driven by the demand side. All the information are more personalized, especially regarding all the passengers, and all these data can be differentiated and segmentations can be done on the top, and then used different strategies to approach the passengers. The other advantage is that it's not only about CDM, which is the total, which is the cooperation between, as I said, ATC, handling, airport, and airlines. But it's slightly moving towards a total airport management, which means that the airport is fully open with its information, not only to incorporating with those 4 stakeholders, but even with the surroundings. We have looked at the Airport 4.0 concept, and we found out that it's not only about to be open and available, I mean, through the data to the surroundings, like to a smart city, and then used the link with the system surrounding the airport and somehow cooperate. It's then more about the modeling. So we've decided to use this current unfortunate situation for airlines and airports when we have a little bit more time than normally, and build the digital twin of the airport. Once you build the digital twin of the airport, you can actually start modeling by using a multiple agents system, which means that this kind of a tool can give us theoretically the opportunity to modulate the system, the interaction between the airport systems and the surroundings. And of course, the main objectives of this modeling is to increase the operational efficiency, environmental sustainability, resilience to be ready for similar crises in the future. And for us, as a Prague airport, not only Prague airport, but even like other airports which are called destination-driven, passenger experience. So we took this and slightly changed the system. When you look at what we've done, it's that can be described that it's actually happening in 4 zones. The first one is airborne movement area. That's particularly the area where the aircraft is moving in the air side. Then slightly a bigger zone, which is the air side. Then, and again, slightly bigger zone, which is the land side, which means there are taxis, buses, and of course electricity, which we are getting, and so on. And then airport region zone, which is actually touching the smart city. And these 4 zones can be modeled by using those agents. Where we are actually aiming is again to increase the customer satisfaction and to use better resources, not only resources of those 4 stakeholders I've already mentioned, but even from the surroundings, from smart city, from surroundings, from villages, and so on, so that we, for example, can model what we have to do as the airport and as the city by using the information when a certain number of the people is traveling to the airport from downtown through smart Europe Street, which is basically the link between downtown Prague and Prague Airport. And we can actually slow down the traffic. We can speed up the traffic. We can check whether we still have passengers on those in those vehicles, and what we can actually do about it. How can we continue working on this in the future? First of all, we have to finish the digital twin, which is almost done. Then the Evropská street has to be digitalized and create a new digital twin so that we can actually link all those systems together. We will develop those agents, and we will modulate different kind of situations. This is something what will definitely bring us the way how we can then develop and help those agents to negotiate through some kind of algorithm. And then based on this theoretical approach, we can actually, as the airport and of course the Prague, as the smart Prague, we can cooperate and satisfy the customers, in our case, passengers. We can lower the cost for both sides and so on. The other thing which I should mention over here, and it's quite important, whenever you start doing or interacting in digital world, it's quite important to invest in cybersecurity. Cybersecurity, it's mainly, and it's been actually done at the airport by building a cybersecurity operations center, which is 24 hours surveillance of what's happening. Because the more you open the airport, more you open the cities, you have to develop this approach, cybersecurity approach. Otherwise, it's going to be very vulnerable. The other thing which we have to look is ontology modeling. The main reason for that is that there is a Prague airport system, but there are a lot of systems surrounding Prague. If you want to link them together, if you want to use agents to work or to negotiate, then there has to be a same terminology. So that's why we have to find out a way how they can actually communicate, because they are developing in their past, which means that they might be a little bit slower, they might be a little faster than the airport. So at the end, what I want to mention is that this kind of research, which is done by Prague Airport and Czech Technical University in Prague, is aiming to satisfy more our customers, to lower the cost and to increase the revenue, which is then a very useful outcome of our cooperation. Thank you very much for your attention, and I'm ready for for questions if there are any. Thank you.
Thank you very much. I found very interesting to hear about the changes that I hope I will experience as a customer this in this Airport 4.0. So good luck with your work. Thank you very much.
Thank you very
thank
much.
You.
Have a good day. Bye-bye.
So that was actually the closing presentation for this session, and we will move directly without basically any break towards the next session. That's not going to talk about modeling, which I found interesting, but we are going to talk about another interesting topic and very important in cities, and that's livability of cities. So I am glad I can welcome my dear colleague Ira Rubenstein, who is going to moderate this session. So enjoy the next presentations. Thank you.